Good morning, everyone, and thank you for coming to our landmark series, Circuits, Terahertz and Beyond. My name is Ted Rappaport, the director of NYU Wireless, and on behalf of NYU Wireless and the Electrical and Computer Engineering Department, it's a pleasure to welcome you here live and also out on the web. Thanks for joining. This seminar series, Circuits, Terahertz and Beyond, is the brainchild of faculty in the NYU Wireless Center, which is supported by a large industrial affiliate program, looking at the future of wireless and where communications, sensing, and computing is going. We have 8 remarkable speakers who are coming to campus here at NYU at the Tandon School of Engineering during this fall semester. A lot of you are taking this for your courses, and the range of speakers are just incredible. We're going to learn a tremendous amount, and it's great to have these leaders as allies, partners, to help us as we hire faculty and build the resources to be a leading player in the future of terahertz. I'm delighted to introduce our first seminar series speaker, Professor Aydin Babakani. I've known Aydin since his seminal PhD work, where he was one of the first people in the world to build on-chip antennas at millimeter wave before people realized millimeter wave was going to be a core part of the wireless industry. Aydin's an entrepreneur. He's a director of the Integrated Sensors Lab, and he's got some great things to share with us about the future of terahertz. Please welcome Professor Aydin Babakani.
Thank you. Thank you, Ted. It's great to be here, and thanks for the invitation. I have to say that I'm very impressed with all the facilities and all the interesting projects going on here. It was really remarkable. And it's great to be here. So what I'm going to do today, I'm going to discuss the research that I've been working on during the last 5-6 years, mostly at Rice University and recently at UCLA. So this is all about really what we can do with CMOS silicon technologies, from terahertz pulse sources to miniaturized spectrometers. So first I will discuss an important paradigm shift that I believe is happening in our field, in the field of integrating complex systems in CMOS. And then I will show you how we are changing the way we need to do the research to actually get the most out of the silicon technologies. And that's how we were able to implement, for the first time ever, terahertz sources in a commercial standard silicon process. So we are able to produce signals at 1.1 terahertz with 1 hertz, 2 hertz frequency line width, without using any lasers. All electronically, you have digital input, you have terahertz out. And then I will explain, okay, now we have all these tiny chips around, how can we use them for wireless synchronization? How we can synchronize a massive network with sub-picosecond timing accuracy, and how we use that for localization, imaging, and all that. And then I will change the topic a little bit and discuss the first electron spin resonance spectrometer that we built that actually detects free radicals and unpaired electrons in various industries. So this is a technology that's commercialized now, actually being used to monitor the level of free radicals in industrial processes. I will show you some of the field experiments on that. And then I will also discuss some of our work in the last few years that we are focusing on wirelessly powering all these complex chips, really removing any wires from the chip. And then try to use medical implants to try to use basically put the chips in infrastructure, in cements, and everywhere. You're going to see some of the examples of that. But let's see what's really happening in the field of silicon. Finally, we are able to demonstrate terahertz radiation from a standard silicon. But if you pause a second here and think about terahertz and the wavelength, you see that the wavelength in air is about, half a wavelength is about 150 micrometer at 1 terahertz. And in silicon, that's even smaller. So that's your radiation component. And you're all familiar with the Moore's law and integrating more and more complexity on a single chip. So if you, for example, you look into a decent low power processor, this is an ARM M0 processor in 40 nanometer process, that's only 85 micron by 85 micron. So if someone gives you a silicon area of 1 millimeter by 1 millimeter, what can you do there? You already put the antenna there. There's a computational chip there. That's your processor. Suddenly, this 1 millimeter by 1 millimeter seems a large area. And so you can actually add more antennas. You can build phased arrays. You can, in some application, you can add functionalization of surfaces. You can do sensing. So this is just really the beginning of this field. We're cutting every wire from the chip. You're wirelessly powering these few sense chip, and you're doing anything from wireless communication to sensing. So what are the key changes? Obviously, the electromagnetic interface to chip becomes very important. You can't afford to give a design of the single circuit component or amplifier to a circuit designer or ask an antenna person to design a 50 ohm antenna. Everything has to be done all together. And as you're going to see that, we are intending to use no wires for clock. You're going to see some of the chips that we are building that we are actually using wireless synchronization down to picosecond. And then beyond that, we are trying to eliminate any wires for providing DC power. So you're going to actually harvest electromagnetic energy, produce a stable DC power, and use that for sensing applications. So when you do this, you see that for the first time, actually traditional design techniques are not necessarily optimum. So, and the reason we are going to see one example is that the direct digital to impulse radiation, for example, is the best approach so far for producing these very broadband picosecond pulses. So when we are looking into or working in this field, there are two sets of applications that are enabled with this technology. The first set is just because you're putting the antennas on the chip, you can move to really high frequencies. So some of the applications are enabled by the fact that we can produce and radiate high frequency electromagnetic signals from silicon. So that enables terahertz and terabit per second comlink. This is an example of a basically true time domain signal that will radiate from the silicon. You're going to see a zoomed version of this. So it's about 1.9 picosecond, decent, nice signal. And then we use it in experiments to produce imaging, where each pixel tells you what kind of material exists. So we're actually working on hyper-spectral imaging system. This is an example of image that we produce. We're working on 3D security imaging and also gas spectroscopy. It turns out that when you have this massive amount of spectrum, you can do so many other things. Like even a single gas molecule vibrates with your EM radiation, so you can use it to probe gas molecules. And then obviously precision time frequency transfer, how to synchronize massive number of drones or nanosatellites. This is all going to need high frequency and terahertz. Now you have that, the question is, okay, a second set of applications are really enabled by the fact that we have these tiny chips that can be synchronized wirelessly, so why not just throwing them around like dust particles, and suddenly you have this massive phased array system at terahertz that's not on a rigid platform. You can stick elements of each array to anywhere you want in the room or on the car, and then suddenly you have a picosecond synchronization between elements, so you can build a massive, large arrays. And now the second set of applications are enabled because we are putting everything on a single CMOS chip. No wires are connected. What does that mean? That means we can send these chips to do sensing in places that were impossible to sense anything before. For example, we are working on tracers for industrial monitoring. We are literally sending these CMOS chips through pipelines in oil and gas industry to reservoirs to do mapping of temperature 10,000 feet underground, wirelessly powering them, put them in the cement to monitor for corrosion, for basically gas leaks and everything. So I guess the vision is that CMOS is going to be in every infrastructure. When you're building these complex systems where each one is few cents, you will use that. You will use that in a lot of places. And obviously, a lot of applications are medical implants. So there are a lot of important applications where you cannot afford to send a large instrument inside the body. So you have to shrink the size to a very small dimension. And that's where I'm going to show you some of the results of our wireless pacemaker, where we're intending to send these pacemakers that are so small through a vein in the leg to multiple locations in the heart and wirelessly synchronize multiple pacing points. And do precision timing of the electrical pulses on the heart. And we are showing the testing in the large animals and how successful this one is. And the last one is really literally terahertz powered smart dust sensors, where there's going to be potentially these chips flying around. They are so light, you can make them fly. And then now you can synchronize them and you can do interesting things with that. So let's now go over some of the key examples of what we have demonstrated so far, and that brings us to the first part of the discussion on picosecond digital to impulse radiators. So if you look into the terahertz spectrum, traditionally, terahertz is defined in frequencies above 100 gigahertz and down about basically 10 terahertz. So in frequencies lower than 100 gigahertz, it's easy to generate signal with electrical methods. And in high frequencies in optical range, energy of a single photon is large enough so you can build room temperature lasers. But when you come to produce any electromagnetic energy in terahertz, these electrical systems are not very efficient, and optical methods need to be cooled down, so optical lasers. So this is one of the challenging areas in our community, how to really produce any signal and do the measurements at terahertz frequencies. But if you do that, you can do a lot of interesting things. You can, for example, look into this different white powder in an envelope. It can be inside the envelope, and you can differentiate if that's what kind of material that is. Is that an explosive? Is that poisonous? Is that not? You can detect a lot of explosive just due to the vibration of basically the rotation of the molecule. And you can obviously build high-speed data links. You can use it for security imaging and all that. So now let's try to look and see, well, why terahertz is so powerful, why people haven't really used it that often, why it's not a mainstream technology. And this slide tries to explain that. So for the last 20, 30 years, the community that actually produced picosecond pulse and radiate that, these are mostly optics community that use a femtosecond laser. This is a relatively expensive laser that produces about a few hundred femtosecond pulses, probably like $50,000, $100,000 big laser system. And then you have to actually build a photoconductive antenna, bias an antenna such that when there's no optical illumination, there's no current. But when your 100 femtosecond optical beam arrives here, you suddenly short the antenna. And then you radiate a beam that's about 1 picosecond in duration. So that's how community in the past produced these terahertz pulses. And then how they detect it, they actually use a subsampling method. So they delay the optical beam mechanically or sometimes electronically, and then use a similar PCA to detect the system. And obviously, you see the problems. There's a lot of alignment issues. You need to use a lot of mirrors. You cannot even scale this to large arrays. So when we thought about this problem, we said, okay, how can we solve this in silicon? Can we use similar methods to produce a picosecond pulse in silicon? And back then, probably the best state-of-the-art published work on silicon pulse was around 40, 50 picosecond. This is where we demonstrated actually less than 2 picoseconds. So how we did that was we were inspired by this spark gap idea. So you build a huge voltage and you suddenly short it, and what happens? And then there was a lot of modification over that. So we ended up using a different idea that actually uses a slot bow tie antenna on the chip. So this is basically the orange color here. So we are passing a DC current around this antenna. So you can think of this as an inductor in DC or low frequencies. So when you pass this, you're building up magnetic energy around it. But now what happens if you have an inductor, but you disconnect the current very fast? Inductor doesn't like that. It's going to generate LDI-dt, which is a large voltage. But that's what we want. We want to generate a large voltage very fast. Because at the same time, this aperture that we have here is not only an inductor, it's actually an antenna at high frequency. So when you produce a large transient of voltage, it's going to radiate. So what you're doing is that you're actually going to store magnetic energy there, you're going to disconnect it very fast, and suddenly you have a picosecond pulse radiated from the chip. So this is a little bit more explanation of how we are doing this. So we have on the chip, we are passing a DC current through a transmission line. There's a lot of little techniques here to how to have a distributed array of capacitors to deliver charge very fast to the antenna on the time scale of picosecond. And then pass it through the antenna. And the only thing you need to operate this is a digital trigger. So this is a standard 200 picosecond digital trigger. You sharpen that down to 30 picosecond and further down to few picosecond. And you just disconnect it. With every rise time of a digital trigger, you have a 2 picosecond pulse that's radiated. And how good is the timing synchronization between your digital and terahertz? That's on the order of 200 femtoseconds. And I'm going to show some of the results that we have. So as you see in CMOS, there are all the practical issues. You need to put wire bond. There's an inductor there, basically, that causes issues. So you need to make sure you have a stable on-chip supply voltage to deliver the charge. And then what we did in the first version, we used a cascade, basically bipolar transistors in 130 nanometer SiGe and also another version in 90 nanometer SiGe. And then the way it works is that you send your digital input. You delay it as much as you want, so you can delay the input digital trigger with resolution of literally 100 femtosecond, with dynamic range of beyond 100 picosecond. And by delaying that, you're seeing that the pulse that's radiated is delayed with exactly the same amount. And then what we do is that we sharpen this with digital buffers down to 30 picosecond and using an analog circuitry down to few picosecond. And then we use that to turn on and turn off this fast switch and do the radiation. So because this is so simple to build, you can easily scale this to an array. So we have an array of 2x4 picosecond radiators on a single chip where you have independent timing control on each radiator. So you can control the timing of each radiator with about 200 femtosecond resolution. And everything works really nice and radiates. And I will show you a picture of this picosecond terahertz pulse radiator all on a single chip. This is basically 2x4 array. It only needs DC bias here and digital input. Nothing high frequency, no laser is used. So you now need to think, okay, when your antenna radiates, how is it going to radiate? The silicon substrate has a high dielectric constant, so that behaves like a low resistor for radiation. It's going to absorb all the energy. So in most cases, we use a silicon lens to couple that energy to air. In some other cases, we just don't use silicon lens. We optimize the thickness of substrate, and we radiate from top side. So one of the very first problem we had was, okay, we are producing these picosecond pulses, but we go buy the best oscilloscopes out there. It can only measure 8 picosecond pulse. What would you do? How do you characterize this? And everything else, including like VDIs, down converters, and all that, they're all banded. There's nothing out there that gives you a single shot like measurements of the entire spectrum. So we had to build that ourselves. So we ended up using, for characterization purposes, an asynchronous laser-based system that actually we only use the detector part of the system. This goes up to 4 terahertz. And these are 2 laser pulses that are, they have a rep rate of 50 megahertz, but they are one of the lasers shifted by a few hertz compared to other ones. So what you do is that you actually detect the pulses at a slightly different shifted frequency than the transmit. So you can do subsampling, and you can quickly capture the shape of the pulse. So what we do is that we take the laser output of this, we do signal conditioning, convert it to 50 megahertz, basically divide that down to 10 megahertz reference signal. We clean that. And now with the 10 megahertz reference, you can lock any microwave source. So you can basically produce signals at few gigahertz rep rate that's locked to your laser characterization system. And then you can feed that to your silicon chip. So these are some of the measurements we got from this array chip. This is actually the real time measured time domain signal that the silicon chip radiates. So if you look into the zoomed version of that, it's a very clean signal. It's about 5 picosecond is this basically time duration here. There's some ringing effect, so it gets reflected from the lens and boundary and all that, but you see everything. And then by playing with the bias amplitude of the, basically bias of the transistor, you can actually do simple amplitude modulation. So this is how we can change the amplitude. We are now hoping to produce 2-3 bits of amplitude modulation on each pulse, and everything is few picoseconds. Yes?
How much radiated power?
So our peak radiated power is about tens of milliwatt. I'll show you the ERP measurement over time. Yeah. It's actually better than the conventional, the expensive laser-based systems in terms of the average power, because they are limited by the physics of their laser by the repetition rate. So they can only put pulse with 100 meg rep rate. So that lowers their average power.
So your average power is like 10 dBm?
No, our peak power is, but our rep rate duty cycle is like 10%. We can go to about beyond 5 gigahertz rep rate. So now by changing the digital trigger, you can actually delay these pulses. I'm here focusing on the zero crossing. So that was a time domain measurement. Now we are trying to build communication systems where you have literally a terahertz bandwidth, but you also want to do beam steering. So in those problems, none of those conventional phase array work. If you use like LO phase shifting, every frequency will be radiated to one direction. If you use like RF domain phase shifting, you pass all that information to RF delay, you have those nonlinear delay components that's going to cause basically AM to PM problems, conversion issues. So we decided to completely separate our timing control from the information channel. So we are sending always a trigger signal that doesn't change its shape based on the information you're putting in, and that sets the time of radiation. And everything else, including information, just comes on the amplitude of the signal. So you can actually build a system that has a terahertz bandwidth, and you can actually delay it with 100 femtosecond resolution. It's a true time delay method. So when we built this system, we were also interested in characterizing it in frequency domain. So if you think about a single pulse, in frequency domain, you have a broader spectrum. But now you can program the repetition rate of this pulse. So that means you can produce a pulse train. So that means in frequency domain, you have a frequency cone. Now the question is, we're interested in characterizing this. We want to know, okay, how stable these tones are. What can we do with that in different experiments? So that's why we built up a characterization system up to 1.1 terahertz using a series of VDIs, down converter mixers with a Keysight spectrum analyzer. So you can now look into actually these pulses, a frequency cone, directly on the spectrum analyzer. So these are some of the results we got. We were actually surprised what we were getting initially, but at 750 gigahertz over like 20 centimeter distance, this is the raw data, includes all the loss, free space, free path loss of the mixer and everything. So we were getting roughly 30 dB SNR at 30 centimeter, 750 gigahertz. When you go down to for the first time, we show that beyond 1 terahertz, we can actually demonstrate a tone using a silicon chip with basically few dB SNR. And you're going to see that we have another version that produces much higher SNR, up to 1.1 terahertz. But one of the remarkable things here was that the line width, so we were able to produce these tones with 2 hertz frequency stability. So these tones are actually very, very, very clean. So you can produce anything you want from 20, 30 gigahertz to 1.1 terahertz with 2 hertz line width. So these are the radiation pattern measurement in H plane, E plane at different frequencies. We characterize all that. And then this is the micrograph of this array that's only like 1.45 millimeter by 1.6. If you zoom into the single element, the majority of the area is really the antenna. You don't have any amplifier, you don't have anything else. This is only a very fast switching network that pushes the whole system into extreme nonlinearity. So we had, this one was done, the array one was done in 90 nanometer SIGI process. So let's see, it's frozen a little bit. Maybe keyboard doesn't, yeah, it's frozen. I guess I'll wait to see what happens. Oh, right. It was thinking, yeah. I think it was listening. There's some delay, so I will just wait. No, I think we have to wait. It has a little bit delay.
While you're waiting, what's the efficiency of that? Like how much input power?
So we are consuming 100 milliwatt DC power. That's a kind of.
And your transmitting is 10 milliwatts.
That's a peak power. Yeah,
power, so-
with duty cycle of a few percent.
Okay.
Yeah. All right, let's see. I'm going to be very careful when I press.
Sir, keyboard problem?
No, okay. So this is right slide now. We're lucky. Yeah. So this is the basically it's another version of the single chip radiator. So when you're putting a single antenna on a chip, everything is a small 550 micron by 850 micrometer, but we can actually push the frequencies even further. If you look into some of the numbers here, we can produce 1.9 picosecond pulse with this chip. And if you look into the EPR spectrum, we have everything from basically 30, 40 gigahertz. The EPR is flat from 100 gigahertz to 200 gigahertz, and then it drops basically when you get to 1 terahertz. That's how it looks. Now, for this chip, now if you look into the spectrum, look at the frequency here. At 1.1 terahertz, we are producing a decent SNR, roughly 20 dB, with 2 hertz line width. And then when you go to lower frequency, 600 gigahertz is now low frequency for the system. So you have basically a 40 gigahertz SNR. So it's plenty for doing a spectroscopy, near field sensing and all that. So the goal is really, okay, how to, and we have the receiver version of that. I will show you some of that. So how to really convert a complex system that's $100,000 to something that potentially a few dollars. It's bulky. This is much smaller, millimeter. This is a slow, has a rep rate of 100 megahertz. We can go up to 10 gigahertz. This is not a scalable. You cannot build MIMO or phased arrays. Here you can easily do that. And this one requires a laser, but we don't need a laser. So now we have this source technology. We are trying to see, okay, can we build a spectroscopy system? So in one of the setups or the projects we had, basically the goal was to build a precision gas spectroscopy sensor. So here's our gas cell. We are radiating this frequency comb with the silicon chip, and we are detecting here. We're trying to see if we can actually probe the rotational spectrum of gas molecules. And this was from 2 years ago, our old gas cell. Now we have a better version of that. But the whole concept worked. We actually demonstrated that. If you look into the theoretical results, the NH3 has an absorption at 572 gigahertz. We clearly can detect that. And it's actually interesting. When you're putting more gas, so these gas molecules hit each other, you're going to expect pressure broadening. That means the absorption curve spectrum gets broadened, and we see that as well. So we demonstrate that as well. H2O has another absorption. It has an absorption of 753 gigahertz. We were able to demonstrate that and detect that. So now we are also using this system for hyper-spectral imaging. That's where we have basically a couple of mirrors and the sample in the middle. So this is an image at 330 gigahertz that the students took from a piece of plastic and metal. This is another image they took from a few basically capsules, put powder in, use the previous name of the lab, and this is the image. One of my favorite ones is this. This is a piece of rock. Basically, you don't see what is inside. The rock is taken from 10,000 feet underground, and companies are interested in see what the hell is inside. Is that oil? Is that chemical? Is that basically water? Can we use different complex EOR methods to push the oil? And that's basically how this hyperspectral image shows. This is a transmission spectrum from 100 gigahertz to close to 1 terahertz. And the yellow one shows basically less absorption. Blue one shows higher absorption. So these blue patterns is probably we have more water content here. and the yellow one is more like oil. And now we are building a setup where you can inject different chemicals and you see how they move inside the rock. It's about 5 millimeter thick, 25 millimeter in dimension, and the resolution of image is roughly 500 micron. Yes?
Sorry, this is a stupid question. So is it, you have the sample and you physically move it?
This particular one is, yes, we moved the sample. We focused them in, we moved the sample to get these high resolution.
It's mechanically moved, and each one you probe
Yes,
different
yes,
frequencies
yes,
and measure them.
yes, yes. And now we are trying to look into other interesting medical applications. So people have published using this, like we use $100,000 system with a medical probe to really look into to do dielectric imaging of skin cancer. It turns out that in melanoma, there's some, due to the change in the dielectric constant of the cancer, people can probe basically a skin cancer. We are working on these problems. A lot of people used it for basically for breast cancer. When you remove the tumor, the question is, can you actually take a terahertz image to make sure nothing is left, or to make sure you're not removing too much? So there's a lot of things that's terahertz's signature. Some of that is primarily due to the water content, but there's also other interesting complex dielectric constant that you can measure. So when you have the ability to measure dielectric constant from 50 gigahertz to 1 terahertz, things are also frequency dependent, so you can classify different tissues. You can actually do a lot of interesting things there. So one of the things we were interested in, we were trying to say, okay, we show that we can actually radiate signal from a single chip. What happens if we have two widely spaced radiators? If we synchronize that with a low frequency digital trigger, what happens to the shape of the signal that's being radiated? Can you combine the radiated time domain signals from two widely spaced radiators? So this measurement shows that. So the top one shows basically a red one is the signal radiated from the top silicon chip about 110 millimeter away. We have another one that radiates the blue one. So if you do the measurements separately, you get these two pulses. If you add them in MATLAB, you will get this black curve. But if you concurrently radiate them, you get the pink one. So it means basically combining in air, spatial combining is almost ideal. But we want to quantify this. We want to know, okay, what is the timing jitter of the combined signal? And that's this measurement that shows we measured about 270 femtosecond RMS jitter on the combined signal. So we had previous ones were all built in silicon germanium process. We had another one in 65 nanometer CMOS. This is a larger array. This is a 16-element array, and it has all the digital components. So it has basically DACs and shift register for controlling the delay, and then terahertz radiator here. The CMOS chip produces a little bit longer pulses, about 14 picosecond pulses. This is when 14 channels are on. And then when 4 channels are on, you see that amplitude basically drops. So you can turn on, turn off more channels to quickly change the amplitude. And basically, this is just a measurement of the time delay. So I have the picture of the CMOS chip, about 2 millimeter by 3.3 millimeter. In CMOS process, we need to comply with a lot of top metal filling. That's why you see these dots here. But you have to verify, make sure you don't have many of them around the sensitive part of the antenna where the electric field is strong. So that's why you have this block fills that we used. So I will now, that was mostly the source technology. Now we have that, we wanted to use this in wireless synchronization of different chips. And why we are motivated with that? For different reasons. One is when you put a large array on a rigid platform, you can't really put it everywhere. Let's look at the car radar application. The bumper is curvy. You cannot put a very flat, basically, array there. So ideally, you want to put these tiny chips on the bumper everywhere you want, and then use wireless synchronization. And then beyond that, you can also place these chips widely spaced, so you can increase the angular resolution. So this is basically shows that the effective angular beam width of an array depends on your effective element spacing. So we looked into this problem from multiple basically viewpoints. In the first chip, we build a continuous wave version of this, I would say, is the sensor node. This is a node that receives a low power signal at 100 gigahertz. It has an on-chip patch antenna that actually captures that, amplifies that, and it locks this to an injection lock oscillator. applies phase shift. You need a phase shift for the array operation. And then it radiates back from an on-chip dipole antenna. So everything on this single chip, you amplify and radiate back a signal at 50 gigahertz, half of the harmonic. So when you do this and you have roughly close to 80 to 100 dB gain, every little coupling from your output to input will cause self-oscillation. So we have to deal with that. So basically, I will show you how we deal with that, but this is zoomed exact dimensions of the patch at 100 gigahertz coupled to injection lock, basically oscillator. We have the phase shifter that covers 360 degrees. And then the output differential transmitter that puts the power on a dipole antenna and radiates. So let's look into the coupling mechanism. When you put everything on a single chip, you amplify, you radiate, how do you resolve the self-oscillation problem? One issue is that, okay, let's start with polarization orthogonality. So the patch, the way it's designed, is only sensitive to electric field horizontally here, and the dipole irradiates electric field vertically. So when they radiate, this is how you can actually improve their near field isolation. But that's not enough. So we use frequency separation, obviously. That's one is 50 gigahertz, the other one is at 100 gigahertz. But again, you have harmonics, and their harmonics couple to each other. So how do you deal with the harmonics? Like at 200 gigahertz, they will have harmonics. So to do that, we used basically ground shield to the patch and optimize the patch so it's only efficient in terms of radiation efficiency in even harmonics of basically 50 gigahertz. So that's 100 gigahertz, 200 gigahertz. And optimize the thickness of the substrate such that the dipole is only efficient in odd harmonics of 50 gigahertz. So if you look into the radiation efficiency, this is the blue one is the one with dipole, and the green one is the one with patch. So even the signal goes to environment, packaging, come back, it won't cause self-oscillation because your radiators are not simply efficient at those frequencies. So compared to two simple dipole, you can increase the isolation by 60 dB on the same single chip. So we build this, we're now trying to test it. Okay, we use a basically horn antenna, try to lock this. There's no wires connected for signal, for synchronization purposes. So it gets the signal at 100 gigahertz and radiates locked signal at 50 gigahertz. Now, when you use the free running on the oscillator, you have this basically a noisy signal that you're radiating at 51 gigahertz. When you turn on your transmit, you lock it, suddenly you look really sharp signal. It's like laser looking like beam. And then you can obviously tune the frequency and do all that. So we get about 400 hertz line width at 51 gigahertz with just wireless locking, no wires used. And now we measure the phase noise of the free running system, that's the blue one, the phase noise of the locked one, which is the red one, and also the phase noise of the wired-based system. So now we want to push this one further step. We want to see, okay, what happens if you have multiple of this? Can you still lock them? And beyond that, can you play with these phases to combine them in air coherently? And this is the demonstration of that. These are two chips about 13 centimeters away. We lock them wirelessly. We adjust their phase shift to the power received at the horn antenna is maximum. So this one was successful as well. So we get about 6 kilohertz line width at 51 gigahertz. So I have the micrograph of this wirelessly synchronized chip. It's about 1.7 millimeter by 3.8. The patch antenna is shown here on the left that received the signal. All the receiver, transmitter, phase shifter, and the on-chip antenna on the right side. So that was the first chip. The second chip, we tried to see, okay, now we are producing these picosecond pulses. Can we build a receiver to actually measure the energy of the pulse and extract the repetition rate? And that's going to give you your clock. So if you send these pulses with 10 gigahertz rep rate, you suddenly have a wireless clock at a remote location with 10 gigahertz rep rate. So that was the idea here. So we do energy detection. The way it works is that basically we use a nonlinear block. Everything is on CMOS. We amplify the signal, and we get the energy of the pulse, and we do basically filtering to just extract the clock. And I'm going to skip some of the circuit details here. These are all published work. So I'm going to show basically the results here. The chip was only 1.4 millimeter by 1.35 millimeter. This is the antenna and all the circuitry. Now let's look at the measurements. So here, we use our own pulse radiator that generates these picosecond pulses and the receiver chip that detects these pulses. The question is, if you use a wired connection from your keysight signal source to your spectrum analyzer, what is the effective phase noise, how good your clock is, and if you completely eliminate wire, you do it wirelessly, how good the signal is. That was the ultimate goal of this test. So in terms of the frequency, we demonstrate that with wireless clock transfer, we can get 30 hertz line width at 3.1 gigahertz. And if you look into the phase noise measurement result, this is basically the complete wireless testing gives you as a phase noise that's almost very close to your source with wired connection. So the blue one is the phase noise measurement. When you completely remove the transmitter, receiver, just use a simple wire. And in the wireless test, this is showing that demonstrate that through air, you can get almost same level of accuracy. And you're limited with the instrumentation, basically sensitivity. Here is the unfiltered clock at the output. You can easily filter this high-frequency signal, and it basically shows that you can get a decent period. This is your output clock. So that was the second method. We tried a few other methods. We also looked into the optical ways of passing this clock. So in this experiment, we used the VXL, modulated this at basically 1.2 gigahertz. And use it for longer distance, you want to probably use optical frequencies. And then what we do is that we use this optically modulated waveform to lock an RF oscillator. So how do we do that? It's shown here. So here is a cross-couple RF oscillator that operates at gigahertz. We use one of the diodes in the cross-couple exposed to optical illumination. So the optical illumination generates electron and holes. The other diode is actually covered with metal. When you do that, you're generating a current that's basically differential at the load of your oscillator. And that frequency of that current is frequency of your optically modulated signal. So that's how you can actually lock many RF oscillators that are widely spaced. So this was really a small chip. Our antenna was basically our diode, which is really small. This is a photodiode for optical illumination. And everything is really, this is the optically locked VCO. That's what we called it. And now if you look into the measurement results, the free-running VCO puts out a spectrum like this. This is the red one. The optically locked produces signal that's really nice and clean. So this just demonstrates that we can actually use optical methods to do that. So for a variety of applications, depends on what your distance is, you can switch to optical ways to synchronize. So now what I'm going to do, I have roughly 10-15 minutes. So what I'm going to do is that I'm going to show some of the other sensor technologies that we have been building by the power of CMOS. We are trying to miniaturize them and then try to actually use them in the field. So I'm going to completely change the topic to electron spin resonance and how it works and how we actually build a miniaturized version of that. So this is a very powerful spectroscopy method. The concept is similar to NMR or MRI, but the difference is here you're probing spins of electrons. And the nice thing is that electrons come in pair in most materials, so they actually don't have any ESR signal. But in some specific materials like free radicals, they have unpaired electrons. So you can actually see unpaired electron. And you're not going to basically see the interference by the water molecules or other things in the environment. So what are the applications? In physics, they actually use it for basically studying the defects or sample composition. In medical application, they use it for cancer applications. When we did that, we were in Houston with a lot of oil companies around us. So we said, okay, what are the applications of this in the oil and gas industry? It turns out that there's this interesting large molecules in oil. They're called asphaltenes. And they have this stable unpaired electron that lasts for millions of years. So this is mostly because of the organic content. Probably dinosaurs died many years ago, and there's some asphaltenes left there. So I don't think people exactly know what the origin of that is. But the issue is it's a huge problem, because what happens is that when temperature drops, it actually blocks the pipeline. And intervention cost us $500,000 for onshore to a few $1 million for offshore. So
Is it possible to do that free radical
Yeah.
Real time?
Yeah.
Real time?
Yes.
What's the processing required to see that?
Well, I'll show you how it works. So you put the sample in the magnetic field, you energize the unpaired electron, you sweep the magnetic field, and you probe it with microwave. So one thing I have to mention is that electron, because it's much lighter than basically proton, for the same magnetic field, the resonance frequency is 600 times larger. So you're actually dealing with microwaves, which is type of the problem we're interested in.
So you can't see it in real time.
Yes.
What's the typical magnetic field used here?
So for a 5 gigahertz system, that's 1500 Gauss, roughly. So 1 Tesla gives you 30 gigahertz. So this is a direct method for probing partial PO2 in cancerous tumor. So a cancerous tumor has a higher level of oxygen activity. So you can actually use this to directly probe PO2, and people have demonstrated that in basically mouse and clinical work. And in pharmaceutical application, you can actually use this to look into the quality of pills. In engine oil, when you use the oil, it generates free radical. So there are some applications there. So what are the challenges? The challenges, very briefly, like how the physics works. So you put the unpaired electron in a magnetic field, and it goes through energy splitting. And then you can actually now probe that with the microwave. So you put a sample in a magnetic field, it goes through energy splitting, you sweep the magnetic field, you measure in a spectrum. But because the signal is extremely weak, that's not enough. You cannot detect it this way. So you have to modulate magnetic field at certain frequency, let's say 100 kilohertz. And then what happens is that the reflected signal that comes back is actually at a slightly shifted frequency. So you're sending, let's say, something at 5 gigahertz, and you're getting back a huge interference at 5 gigahertz, but 100 kilohertz away from that, you get your actually signals from your electrons. So it's a huge self-interference problem. It's similar to the full duplex problem that people are interested in wireless communication. So basically, but the concept is similar. You send a transmitter signal to the sample, you have a circulator, but you get your undesired signal that's extremely weak. But your direct coupling from transmitter to receiver completely blinds your receiver. In conventional system, you cannot use it. You cannot detect it. So we build a chip to completely solve this full duplex issue. So there's basically a transmit that puts out the microwave signal at 5 gig. Everything goes to the sample, comes back. The desired signal is slightly shifted from your 5 gigahertz, about 100 kilohertz shifted. So you cannot directly inject your canceling signal at the beginning because you will completely degrade the noise figure of your receiver. So we have to amplify it by a little bit, 10 dB here, and then add the phase and amplitude control to cancel the interference, and then further amplify that. So that was the complete chip for this ESR transceiver. It has the active cancellation, all again, and this one is by CMOS process. And here it shows that we can improve across all frequency range from 4 to 4.6 gigahertz, and across all the phase numbers, the isolation we are achieving is more than 30 dB. And when you do that, your receiver conversion gain at a high level of self-interference and signal can be still very high. So it's not going to blind your receiver. So a very important plot is noise figure, how much degradation you have on the noise figure. This is a black one is a noise figure of receiver when transmitter is completely off. When you start the active cancellation, you have a small degradation. If you now turn on your transmitter on the same chip, you're going to huge interference, you're going to huge degradation noise figure. And that's what's bad in full duplex systems. When you turn on your active cancellation, you reduce that down to basically reasonable numbers. But anyway, the summary is that we build a system, we miniaturize the magnet to something that looks good, looks small like this. All the electronics are on a single chip. And the whole system is commercialized, actually being right now used in West Texas on oil fields. So whatever they produce, we can go and see basically the level of asphaltenes that come to surface on your cell phone, basically. And this system can detect corrosion ions in the flow. It can go to 5,000 psi, 175 degrees C, and all that. So now what I'm going to do is spend 2-3 minutes on our medical implants and wirelessly powered chips that we are using for wireless pacemakers. And here completely different topic, like what are the problems of a pacemaker and why we are interested in this issue. So if you look into the heart, electrical system of the heart, it's actually interesting nonlinear electrical system. So the way it works is that you have a central node, it's called SA node. First, the heart electrical signal initiates from that, and it's distributed through different part of the heart muscle. In a healthy person, everything works, everything is nice, but sometimes what happens is that the delay of the signal that goes to different part of the heart is not same, so different parts of the heart actually pulses at different time delay, so your pumping efficiency is not good enough. So companies like Medtronic use this lead-based system. This is a huge battery-powered pacemaker with a huge wire that has to go through all these veins and blood, go to inside the heart to just deliver a current to synchronize the heart. So that has a lot of infection problems. They recently built a smaller one that actually doesn't have lead, but it still has a battery. If battery is depleted, they have to go through another surgery and replace it. So what we were interested in is, can we build a battery-less, lead-less, wirelessly powered microchips to get the power wirelessly, but produce enough energy to actually control the beat rate of the heart. And this was our first pacemaker that was operating with on-chip antenna at higher frequencies. But what happens is that if you look into the natural sinus rhythm of the heart, this one is, I think, in a pig at 102 beats per minute. If you pulse the signal at a frequency less than this, heart doesn't respond. But if you pulse the signal at a frequency higher than this, you can actually lock the heart. So you can control the period of the frequency of the heart. So this is a complete, this one, we increased the heart rate to exactly 120 beats per minute that was programmed, and again to 172 beats per minute. So this one was successful. The problem with the first chip was when the way it operated, it harvests electromagnetic energy, puts it on a cap and releases it. When it gets to a certain level of energy, it releases. So that's not good, because if you bring your transmitter, it's going to put more pulses. So we fixed that in the future versions. We demonstrated wireless pacing from 2 different sides. But in the latest experiment, we used actually 6 different tiny chips on the heart and demonstrated that we can synchronously do the wireless pacemaking. And we even closed the chest. We demonstrated that, yes, electromagnetic energies at those frequencies can penetrate through several inches of the tissue, and you can build a wirelessly powered pacemaker. So the core circuitry is only 200 micron by 1 millimeter. We used it for sciatic nerve stimulation to control the movement of the leg. We put that in deep brain stimulation in mice. So this is a really happy moving mouse here. There are 2 of them. We use a single transmitter to control the electrical activities deep in the brain, to look at their behavior, how they move, how fast they move, how we can control that. And now we have a really low-powered electrical recorder that only consumes like 2 nanowatt per channel. And we are trying to shrink it further to get to the cell size, that's where we are trying to use optical ways to basically provide energy to the chip using these surface grading apertures. So the last slide really here is showing that, okay, what's the future? What are the directions we are taking? The way we are looking is that, yes, these CMOS chips will be almost everywhere in the battlefield, in the environment. You're going to have, they're so light, you can make them basically with very little energy to fly. So in the room, you're going to have tons of these CMOS chips. The question is how to use them to do synchronization, imaging, sensing, and all that. And eventually how to couple that with self-assembly techniques to do precision biomolecule detection or DNA detection. So this is basically kind of the trend. And I'm just a speaker here, so all the work was done by students and postdocs. And I'm going to skip the conclusions, and hopefully I was convinced to show that, yes, the CMOS provides a really massive platform, but you have to think a different way, how to use that to something beyond communication, and how to do this basically interesting sensing. And thank you very much for listening to the talk. We have some time for questions. Thank you.
Professor Babakani, thank you for this truly remarkable lecture.
Thank you.
What you've done in inventing the future of terahertz, creating measurement systems to see what we've never been able to see, to use wireless to synchronize, to create resolutions we've never seen in the world. I'd say you're a true virtuoso of circuit design. Wouldn't you say a virtuoso of making the future? Let's give him a hand.
Thank you. Thank you, everyone.
So in conclusion, with the first seminar, we'd like to present you with something. I'd like to ask Dr. Ivan Selesnik, the ECE department chair, to give you a presentation.
Oh, thank you very much. Thank you.